These are the notes for section 7.1, part A. So you should have your note packet out and then bring it into class tomorrow, and I'll just check off that it's done for the homework points. So in 7.1A, our goal, I'm going to go ahead and write this down here. Our goal is to find the area of a region between two functions, or between two curves, if you want to put it that way. And last chapter at the end we were talking about how to find the area between a function and the x-axis, and remember we said that if you're doing that between the boundaries from A to B, you simply just find the integral and you watch for where it falls below the x-axis and you make that positive. But basically we can say that the area beneath the curve and the x-axis can be found by integrating. Remember, the reason for that was that this dx is actually change in x, and it represents kind of the width of a very tiny rectangle. F of x represents how high the function gets. And when we integrate, what we're doing is summing up an infinite amount of them, and what that does is it ultimately gives us the area beneath the curve. Well, in this section, what we're going to have are two functions. So I'm just going to draw one here in red, and I'm going to label that f, very similar to over here. I'm just going to blow it up. Then I'll do another one over here, and I'll call this function g. And our goal is going to be to find the area between those two functions. So we're going to go shade that in there. I think I'll try to maybe make it, I wonder if there's a way I can, we're going to try something here. Use some yellow. See if I can shade this in so it's nice. So let's go shade this in. Our goal is going to be to find the area between these two functions. Perfect. We'll go like that. So what we're going to do is we're going to take that rectangular approach again. We are going to sketch a rectangle that has a width of what we call delta x, or change in x. So I'm just going to grab one rectangle in here. I'm going to kind of head over and down. And when we talk about delta x, we're talking about the change along the x-axis here. And we eventually make that infinitesimally small, and we add up an infinite amount of them. But for our purposes here, we are just going to go ahead and sketch one of them. So the width of a rectangle is delta x, or dx. And our concern is going to be, well, what is the height of this rectangle? Well, I'm going to take and just make a fake point here. I'm going to say, let's suppose this x sub I, whatever it is, let's suppose it's maybe 5. And let's say that the red function, or g, at 5, let's suppose g of 5 is maybe 1. And let's go up here and let's say f of 5 is, let's say, 7. Well, you can obviously tell that the height of the rectangle is the change in these y values, which would be 6. Well, how do we write that with the functions? Well, what we do is we take the upper function's y value and subtract the lower function's y value. Well, my upper function up there is the blue one, which is f. So it would be f of x minus the red function, which is g of x. And that would give me the height of the rectangle. So when this says what Riemann sum could we set up to find that area. Remember, Riemann sum is just basically adding up all those rectangles, but what we do is we add up an infinite amount of them. And we take the sum as I goes from 1 to n, and what we do is we take every rectangle and we find its area. Well, how do we do that? Well, we find the height of every rectangle, and we multiply it by the width of every rectangle, which looks like this. Well, in ours, our height is actually the difference between f and g. So if I take the height of all those rectangles and multiply them by the width, I will get the total area. Well, let's transfer this into our integral notation. We talked when we first started doing these that this whole notation is really the definition of a definite integral. It's a sum. That's kind of where the symbol goes from. And we put our limits on here. Where are we summing from low to high? And we are going to be doing all the f of x minus g of x. Basically, that's just the height of all those little rectangles. And we're going to be multiplying them by the width, which is basically our delta x. All right? And this is really our height. So it's really just adding up a bunch of rectangles. As long as F and G are continuous, and that's kind of our hypothesis for almost everything we do in here. I think every theorem it said it has to be continuous. And as long as we're considering F as that upper or higher function, that's what it means when it says F is greater than or equal to, it's the one that's higher up, then we can use f of x minus g of x as our integrand. If they don't fall above the x-axis, we can still have this same setup. Well, why is that? Well, instead of taking a theoretical approach here, let's just kind of take a numerical approach. Suppose my functions, I'll make some ugly ones here, look like this. And this is f, and this is g. Well, you're thinking, well, this fell below the axis, what do I do? And it's negative. Well, watch it fall out anyway. And again, let's just take a pretend point so you can see what's happening. Let's suppose this is at 3, 8, and this over here is at 3, negative 3. Well, when I do my f of x minus g of x, the height of the rectangle, I get 8 minus negative 3, which gives it a height of 11, which is still positive. So as long as that f function is on top, it doesn't matter if you drop below the x-axis, because you're still going to be finding that distance. And when you subtract a negative, you end up getting a positive. So you don't really have to worry about that case. So what we have here is we have a way of finding the area regardless of where f and g fall, as long as we consider f the higher function. And what we do is we integrate between our bounds, and we do f of x minus g of x, high function minus low function, gives us the height of the rectangles, and we multiply each of those by the width, which we call d of x, dx I mean. So this is very important for us. This is one of 3 key things we're going to be working with in Chapter 7. You do need to know how to find the area between 2 curves. So when we're first starting off here, I believe that on this one, this was shaded in here. All we want to do first of all, and I just took some evens from the book, and you're going to be assigned the odds. All we really want to do first of all is just set up the definite integral that gives you the area. So I'm going to write A equals. First thing we need is our limits. I'm going from negative 2 to 2 or 3. It's hard to tell on there. Looks like it's from negative 2 to 2. Let's negative 2 to 2. First thing I need to do is decide, well, what's my upper function? Well, it's the linear one, which is, in this case is the y2. So it would be 2x plus 5 is the upper function, whatever that might be. Then I subtract the lower function, which in this case is y1, or the parabolic function, which would be x squared plus 2x plus 1. And I take that whole integrand and multiply it by dx. So if I were to clean that up, I'm not going to evaluate it, but if I cleaned that up, it looks like I would get a negative x squared. The 2x is going to cancel out with the minus 2x, and I'll have a 5 minus a 1 or a 4. So my integrand, that's as good as it gets. It just says to set it up. It does not say to evaluate it. So let's go to the next one. We've got a cubic function, an odd function, and we've also got a linear function. So basically with this one, you can do it 2 ways. If you are going to go all the way from negative 1 to 2, then you need to have a summation of 2 different integrands, because from here to here, we've got the cubic one on top, and from here to here, we've got the linear one on top. So you'd have to split it up. What I would suggest doing with one like this, because these are symmetrical, I'm just going to find this one and then double it. And what I'll have is the whole thing. So what I'm going to do here is I'm going to say, well, my area is equal to twice the integral from 1 to 2. Well, who's the upper function between those 2 boundaries? The linear one, or y2. So I'd have x minus 1 minus the lower boundary. And I'm going to integrate that with respect to x. And I lost my integral symbol in there. So there we go. Very straightforward. So next one up, I'm going to be finding the area between 2 curves. So I'm going to have to set it up. I'm going to have to graph it. Usually you're allowed a graphing calculator for these, so if you need it to help you graph, go ahead. But these are so easy, we're just going to go graph those by hand. So I'm going to graph my first function, which is a parabola with a vertex at 0, 2. It's going to go through 1, 3. Let's do that. 2, 6 is nice. parabola like this. That's my first function in blue. Y equals negative x is your line with a slope of negative 1. All right, I'm supposed to find the region bound by those between x equals 0, I'll do that in green here, x equals 0 is actually my y-axis, and x equals 1, which would be this boundary. So I'm looking for the area between these two functions over that interval. Well, let's set up our area formula to find the area between these. And again, it shouldn't be memorized. It's a Riemann sum. It's a sum of a bunch of little rectangles. Well, how tall are they? Well, they're the difference, or the distance between the blue function and the red function. So I'm going to sum up, and on this one I'm going from 0 to 1 on the x-axis, and I need to have the blue function, which is on the top, the parabola, minus the lower function, the line, dx. Well, I'm going to clean up that integrand there, and when I do, 0 to 1, I get x squared plus x plus 2 dx. And this one I am going to evaluate. If you could use a calculator, you would math 9 it, but this one's easy enough to integrate by hand. So I'd have x cubed over 3 plus x squared over 2, using our basic power rule for integration, times twice x. And I'm going to use my fundamental theorem of calculus here. All I need to do is put the top boundary in, since the bottom boundary is 0 for this one. It's wipe all those x terms out. So it looks like I'm just going to have a 1/3 plus 1/2 plus 2, which is 2 5/6, or you could write it as 17/6, whichever you prefer. All right, so let's move on to the next page here, and we are going to take a look at these. It says, and again, I just grabbed some evens. You're going to be doing the odds, so you can refer to these when you do your odds. It says the integrand is given as the difference of two functions, and you're just to sketch the graph and shade. So no evaluating. I've got two functions here that I'm subtracting. I'm going to call that one y1, just so you can see, or you could call it f or g or whatever. And I'm subtracting another function, and that function is x over 3. So basically what I have here is a cubic function and a linear function. I'm going to be finding the area between them over the interval from 2 to 3. Now that's a really small interval, so you know, and usually you'll have a graphing calculator on the AP for these, or you will be actually given the graph and you won't have to bother with graphing. So I'm going to go sketch a graph here as best I can. I'm going to really make the x-axis elongated and exaggerated because I'm going from 2 to 3, so I kind of want to gap that out so I can see what's happening. Well, the blue function, the linear one's easy enough to graph. It goes through 0, 0, and it has a slope of 1/3. So the linear function is heading like this. For the cubic one, if I were you, I would take out your graphing calculator. So I'd pause this, go get your graphing calculator, and do a graph of it. And you're going to see that it goes like this. And then what happens is it kind of comes down like this, and then goes up. And you are to find the area between 2 and 3. So you would be actually finding this region. Now sometimes on your graphing calculator, what you might want to do here is trace over so that your bleeper is right, is that a word? Your blooper, that little thing that kind of bleeps when you hit the trace function, go over into this area and then go to your zoom button and hit zoom in so that you can really see what's going on in this small region of the graph. And that's what I would suggest you do. I wouldn't go bother setting the window, I would just go zoom in on it. I'm going to stop this video and I'll have another one that'll be about 5 minutes long that you're going to need to watch as well.